The central limit theorem says that if you take the sample of the mean of a bunch of samples, it's going to approach a normal distribution. Okay, and that's important because if it approaches a normal distribution, well, we can use our standard normal distribution chart. So to find our z-score, not to find our z-score, well, yes, to find our z-score and to be able to use that chart, we actually now have two formulas. This one right here, where we take our sample mean minus our population mean and divided by the standard deviation over the square root of the number in the sample, or we have the one we've been using for our z-value, mean minus population mean over our standard deviation. So how do you know which one to use? Well, you're going to use this one right here, where that you have that sample mean at the bottom, and you have your sample mean here and your square root of the size of the sample here. You're going to use that when you're talking about a sample mean. And this kind of gives it away right here, okay? You're going to use your normal z-value, the normal formula for finding the z-value when we're talking about individual data. Okay, so if it just talks about an individual person or an individual piece of data, then we're just going to use that normal z formula. So let's look at an example between the two formulas. So let me just move this out, and that'll make more sense in a second. It says the average number of pounds of meat that a person consumes per year is 218.4 pounds. Assume that the standard deviation is 25 pounds and the distribution is approximately normal. Part A says find the probability that a person selected at random consumes less than 225 pounds per year. So what formula are we going to use? A person selected at random. A person. So if we're talking about just one person, we're going to use our normal formula, our original formula. So again, what we're trying to do here, if you look at it, again, it says approximately normal. It says that the average number of pounds a person consumes is 218.4, and we want to know that this single person right here consumes less than 224. So we're looking for all the data over here. So our z-formula, our z-value formula, we take the sample, or the mean, minus our population mean divided by our standard deviation. So it's 224 minus 218.4, sorry, and then divided by our standard deviation of 25. When we do all this, it works out to be about 0.22. So then you look on your cumulative standard normal distribution chart, and that works out to be 0.5871, or 58.71%. So the probability that a person selected at random consumes less than that would be about 58.71%. Now look at part B here, and that's actually on the last page of your notes. Same problem, just part B. It says this, now it says a sample of 40 individuals. So now it's giving you a sample. It wants the mean of that sample. That's when we're going to use our formula for the sample means. So our, believe it or not actually, we're going to use the same normal distribution. This is still the same population mean, and this is still what we're looking for, less than 224 pounds. But what changes is our formula. We're taking the sample mean minus the population mean, and then we're taking the standard deviation and dividing it by the number in our sample. So still 224 minus our population mean of 218.4. So far exactly the same. The difference comes here. Our standard deviation is 25, but we're going to divide it by the number in our population. The square root of the number in population, or our sample, I'm sorry, is 40. When you do that, figure that all out, that's going to kind of, well, it's not going to kind of, it's going to work out to be about 1.42. So we are to the right of our mean. So when you look, you want to use the positive values, 1.42 on your chart. And that gives us 0.9222, or 92.22%. So for part A, The probability that a person selected at random consumes less than 224 pounds is 58%. For part B, if we have a sample of 40 individuals, the probability that the mean of the sample will be less than 224 per year is 92.22%. We use the same numbers and we've got pretty dramatic difference here. Why is that? Well, that's this part down here, okay? The distribution of sample means is much less variable than the distribution of individual data values. If you're just randomly selecting a person, that's going to vary a whole lot more than taking a group of 40 people and finding the mean of them. You're kind of taking that variability out of it, because you've already, however these 40 people, however random they are, you're taking the average, you're taking the mean of them. That's why this number in this case is so much bigger. They're so much bigger. The probability is so much bigger. It's because this one's going to vary a lot depending on a person. But when you're taking the mean of a bunch of people and then figuring it out, your data's a little bit more reliable. Or you could say it's just much less variable. Either formula, though, is going to, depending on what you're looking for, is going to be able to help you to find out that probability. And it's doing the same thing. It's just this new formula here is dealing with samples. So we're taking the samples, mean of a sample, a bunch of samples, instead of individual data.